Myself, Dr. Naresh Kumar, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I want to discuss a very interesting differential equation, partial differential equation, that is known as a Lagrange linear partial differential equation of first order and first degree. So I am going to discuss how we can solve Lagrange's linear partial differential equation of first order and first degree. Which method we apply in this partial differential equation of first order and first degree so that we can find the solution. So I want to discuss in detail about the method which we applied to solve Lagrange's linear partial differential equation. So the name of my topic is Lagrange linear partial differential equation of first order and first degree. First of all, I want to tell you the general form of Lagrange's partial differential equation of first order and first degree is given as below. So the partial differential equation is capital P. This is capital P and this is small p. Capital P into small p plus capital Q into small q, and in right hand side is R. Capital P into small p plus capital Q into small q equal to R. This the general linear differential equation known as a Lagrange partial differential equation of first order and first degree. Here, where capital P, capital Q and capital R are the functions of x. P is the function of xy, functions of x and y. P is the function of x, y, z, and Q is also function of x, y, z, and R also function of x, y, z. So capital P and capital Q and capital R are the functions of x, y, z. So in function P, there may be three variables x, y, z, and small p. What is small p? Small p is dou z over dou x, and small p and small q is dou z over dou y. Okay. So small p is the differentiation of z with respect to x, and small q is the differentiation of z with respect to y. Solution procedure of first order Lagrange linear partial differential equation. Lagrange linear partial differential equation is Pp plus Qq equal to R. Pp means capital P into small p plus capital Q into small q equal to R. This is equation 1. How we can solve this Lagrange linear differential equation, linear partial differential equation of first order? How we can solve? Which method we apply in this differential equation to find solution of the equation 1? So I am discussing here first of all working rule. Okay. So working rule. What is work we are doing here? So step 1, we are dividing the procedure in several steps to making easy. So step 1, write down the auxiliary equation of 1. First of all, question is given in the question paper, that is the form of 1 means PP plus QQ equal to R. Then in step 1, write down the auxiliary equation of 1. So auxiliary equation is dx upon capital P equal to dy upon capital Q equal to dz upon capital R. So basically in auxiliary form, this is equation 2. Basically in auxiliary form, there are 3 fractions. This is fraction 1, this is fraction 1, this is fraction 2, and this is fraction 3. There are 3 fractions and all fractions are equal to each other. There are 3 fractions, fraction 1, fraction 2 and fraction 3. In the auxiliary equation of 1, and all fractions are equal to each other. So what is step 1? Step 1 question is given in our question paper. That is in the form of general Lagrange linear partial differential equation of first order and first degree. That is capital P into small p plus capital Q into small q equal to capital R. This is equation 1. And any question given in our question paper, then we compare to equation 1, then we can find value of capital P, capital Q, capital R. Okay. Now the formula for auxiliary equation of 1 is dx upon capital P dy upon capital Q equal to dz upon capital R. This is auxiliary equation. There are 3 fractions, fraction 1, fraction 2, fraction 3. 3 fractions. Fraction means numerator and denominator. In any term, if there is numerator and denominator, then that term is known as a fraction form. So there are 3 fractions and all fractions are equal to each other. Step 2, solving equation 2. This auxiliary form known as equation 2. Solving equation 2, taking any 2 fractions are equal. Out of 3 fractions, all fractions are equal to each other. Then solving this. So how we can solve this auxiliary equation? So we are taking at a time any 2 fractions are as equal. Either fraction 1 equal to fraction 2, fraction 2 equal to fraction 3, or fraction 3 equal to fraction 1. So we get here 3 relations. So out of 3 relations, in step 2, we solve any 1 relation, any 2 relation. So we are taking any 2 fractions as equal. So now in equation 2, we see that there are 3 relations of fractions. 3 relations of fractions. Like as below, dx upon p equal to dy upon q. This is first relation. First fraction equal to second fraction. This is relation 1. And relation 2 is dy upon q equal to dz upon r. Second fraction equal to third fraction. And relation 3, dx upon p equal to dz upon r. First fraction equal to third fraction. So we get here 3 relations in the form of fraction. Okay. Here we will solve any 2 relations, not all 3. Any 2 relation we have to solve here out of 3. Then we find solution u equal to c1 and v equal to c2. This is equation 4. Step 3 is then f u v. We write the solution in this form. Function u v equal to 0. Or we can write this solution in other form. Another form means u is the function of v. U is some function of v. This is first solution u, v is second solution. So first solution is the function of second solution. We can write this type. And another form is function u b equal to 0. This is complete solution of equation 1. U is the first solution, which is finding any taking one relation. One relation means fraction 1 equal to fraction 2. B is the second solution, that is finding second relation, either fraction 2 equal to fraction 3 or fraction 1 equal to fraction 3. So we solve any two relation out of three relation. Then we get first solution U and second solution B. Then we find here complete solution FEV equal to 0. This is the first type to write the solution. Other type, U is the function of V. So this is the complete solution. This or this. Any one form we can write here. Three cases applied to find the solution of general Lagrange linear partial differential equation. Three cases applied here. We apply three cases to solve Lagrange partial linear differential equation. So this equation is Lagrange partial linear differential equation. PP plus QQ equal to R. This is equation 1. Here P is dou Z over dou X and Q is dou Z over dou Y. Here we will discuss about case 1 in detail to solve equation 1 this. PP plus QQ equal to R. This is equation 1. Now what is case 1? Case 1. All questions comes in this case 1 which verify the condition of case 1. So in this case we see that each fraction which is given in the question should be variable separate. First of all, question is given in our question paper and comparing the question with general equation of the Lagrange partial differential equation, then we can find the value of PQR. After we finding an auxiliary equation of 1, that is dx upon capital P equal to dy upon capital Q equal to dz upon capital R. So this is known as the auxiliary equation of 1. Now putting the value of PQR in auxiliary equation. So next we see that in case 1, in each fraction the variables are separate. Variables are separate means we are taking any two fraction as equal, fraction 1 equal to fraction 2. Then we can integrate easily if variables should be separate here. Okay. So variables should be separate, then finding any two solution from any two relation is given in equation 3. Now we want to solve here some problem based on Lagrange linear partial differential equation of first order and first degree. So here problem 1 based on case 1. What is case 1? Case 1, we see that in auxiliary equation of given question, the fractions, each fraction have variables separate. So solve the following partial differential equation by Q minus XP, here is XP equal to Z. This is question. By Q minus XP equal to Z. This is question. Okay. This question is given in our question paper. So now solution. First of all, we write this equation. By Q minus XP equal to Z. This is equation 1. But our equation is PP plus QQ equal to R. But in our question is first is small q, then is small p. But in question small p is first and q is last. So general equation of the Lagrange partial differential equation is given as below. Capital P into small p plus capital Q into small q equal to R. This is equation 2. Writing equation 1 as equation 2. What is changing in equation 1 and 2? In equation 1, there is Q first and P last. And equation 2, P first and Q last. So, the given question writing as equation 2. Writing equation 1 as equation 2. So, I am writing minus xp, P first and plus yq equal to z. This is equation 3. And capital P small p plus capital Q into small q equal to R. This is equation 2. This is general Lagrange linear partial differential equation of first order and first degree. This equation. Now comparing in both. Comparing in equation 2 and equation 3, then we get the value of PQR, P, Q and R. So what is capital P? Capital P is minus X. Capital Q is Y and capital R is Z. This is equation 4. Now we know what is auxiliary form of equation 2. Auxiliary form of equation 2 is dx upon capital P, dy upon capital Q equal to dz upon capital R. This is equation 5. In auxiliary equation of equation 2, there are 3 fractions. Fraction 1, fraction 2, fraction 3. Okay. But in case 1, each fraction have variables separate. Then we are making 3 relation. Fraction 1 equal to fraction 2, fraction 2 equal to fraction 3 and fraction 3 equal to fraction 1. So we are making here 3 fractions, 3 relations, and we will solve any 2 relation out of given 3. So here now finding auxiliary form of equation 3, putting value of PQR in equation 5. In equation 5, what is equation 5? Equation 5 is general auxiliary form of equation 1. Equation 1, capital P, P, capital Q, Q is equal to R. This is equation 1. And its auxiliary form, dx upon P equal to dy upon Q equal to dz upon R. This is general auxiliary form. Okay. So now in our question, value of PQR is given. So after comparing our question with general equation, then we get value of PQR. So we get here P, capital P is minus X, capital Q is Y and capital R is Z. After putting value of PQR in 5, then we get this dx upon minus X, dy upon Y and dz upon Z. These are equal to each other. This is equation 6. Here we see that in equation 6, each fractions are variable separate. What is variable separate? This is fraction 1, this is fraction 2 and this is fraction 3. F for fraction. So this is numerator and this denominator. How we can say that each fraction have variable separate? So in numerator is dx. Dx means integration with respect to x. And in denominator is function of x only. Here in denominator is dy. And in numerator is dy, integration with respect to y. And in denominator is y only. In numerator is dz, integration with respect to z, and in denominator is z only. So we see that in equation 6, each fraction has variable separate, means we can integrate easily to each fraction. So we are making relations between these fractions. First relation, fraction 1 equal to fraction 2. Second relation, fraction 2 equal to fraction 3. And third relation, fraction 3 equal to fraction 1. So we are getting here 3 relations. And any 2 relation we will solve to find solution. If we solve first relation, then we find value of u, and after we solve any other second relation, then we find value of b. So complete solution is u be equal to 0. Okay. So here we see that equation 6, each fraction are variable separates. So here case 1 apply. If variable are not separate, then case 1 is not apply in our question. So here we are making 3 relations. Relation dx upon minus x equal to dy upon y. This is relation 7. dy upon y equal to dz upon z. This is relation 8. dx upon minus x and dz upon z. This is relation 9. Okay. So now solving any 2 above relation, any 2 relation we want to solve here. Then we get 2 solutions. First solution is the function of second solution. We can say this. Taking first and second fraction, then we get here. So dx upon here is minus x. dx upon minus x equal to dy upon y. This is equation 7. Integrating on both sides to equation 7. So here integration this, integrating dx upon minus x equal to dy upon minus y plus y. Now minus is common, 1 upon x dx equal to 1 upon y dy. So minus integration of 1 upon x is log x. And integration of 1 upon y is log y. And plus adding here constant log c1. So this term taking this side. So here is log c1. This equal to log x plus log y. Okay. Apply here formula. Log m plus log n. This equal to log mn. So here log c1. This equal to log xy. Log is cancelled. So we get here solution c1 equal to xy. And this solution is u. So we get here u equal to xy equal to c1. So this is first solution of the given question. So we are writing dx upon minus x equal to dy upon y. Integration of this is constant, arbitrary constant, log c1 minus log x equal to log y. This log x taking this side, then we write here log x plus log y equal to log c1. Here apply formula log m plus log n. This equal to log mn. This formula apply here. So here is log xy equal to log c1. Log cancel out. We get xy equal to c1. This is first solution. This is represented by u. Xy is equal to u is equal to c1. This is equation 10. Now finding second solution. So we will take any 2 other fractions from given equation 7, equation 8 and 9. Any equation we take. So here we take equation 8. dy upon y equal to dz upon z. This is second relation. Integration equation 8 on both sides, then we get dy upon y integration dz upon z plus adding some arbitrary constant. So integration dy upon y is log y equal to log z plus log c2. Log z taking this side, log y minus log z, log y minus log y minus log z equal to log c2. This is second solution. So we write here other arbitrary constant. First solution be adding c1 and second solution be adding c2. So log y minus log z equal to log c2. Here formula apply y upon z equal to log c2. Which formula apply? Log m minus log n equal to log m upon n. This formula is applied here. M upon n. So here log y upon z equal to this. Log is cancelled. Y upon z equal to c2. This is v. This is another solution. We consider as a v. So log y minus log z equal to log c2. Here we can write log y upon z equal to log c2. Log is cancelled. Y upon z equal to c2. This is equal to b. Now complete solution of 1. First solution is u in last relation and second solution b in second relation. So now complete solution of given question f u v equal to 0. Function u and v equal to 0. This is complete solution. So putting value of u and v here. U is xy. What is u here? U is xy. What is v here? Y upon z. So writing here function xy comma y upon z. Function u comma v. Function u xy comma y upon z equal to 0. This is complete solution of given question. Or other form, we can write other form answer. We can write second form of the solution. Second form of the solution. First solution is u. First solution is u. This is the function of second solution b. We can write this form. U is the function of v. This procedure we apply in Monge's method. We can apply also in Charpit method. This result. First solution is the function of second solution. So this is also complete solution. U equal to function of b. U is xy and b is y upon z. Function of y upon z. So f u v 0 and fxy upon y upon z equal to 0. Or u is xy equal to function of y upon z. Both are correct solution here. Now I am going to solve problem 2 based on case 1. This is also very interesting problem. This question based on Lagrange linear partial differential equation of first order and first degree. So solve question is given this: y square p minus y cube equal to x z minus 2y. Here x y cube. Okay. Solution start. I am writing again question here. Y square p minus xy cube equal to x z minus 2y. This is same question which is given in our question paper. I am writing as equation 1. Now general equation of Lagrange partial differential equation is given below. This is general equation of Lagrange partial differential equation. PP plus QQ equal to r. This is equation 2. Comparing in equation 1 and equation 2, then we get value of PQR. Value of PQR. Okay. So P is y square, Q is minus xy, and R is z minus 2y. R is z minus 2y. Z minus 2y this. This is equation 3. Now auxiliary form of equation 2 is. Equation 2 is general partial differential equation of Lagrange. Equation 2 is Lagrange partial differential equation. So now auxiliary form of equation 2. So auxiliary form is dx upon p equal to dy upon q equal to dz upon r. This is equation 4. Now finding auxiliary form of equation 1. Equation 1 is our question. In our question, the value of PQR is known. So after comparison, our question with general Lagrange linear differential equation, then we get value of PQR. So now putting the value of PQR in equation 4, then we get auxiliary form of question 1. So we get here dx upon y square. Y square is p here. Y square is p. dy upon q. Q is minus xy. And dz upon z minus 2y. This is equation 5. Here we see that in each equation, first two fractions are variables separate. So here case 1 apply. In first two fraction this and fraction this, variables are separate. So here we apply case 1. But we have 3 relation in 5. So now relation 3, first relation dx upon y square equal to dy upon minus xy. dy upon minus xy equal to dz upon x minus 2y. dx upon y square equal to dz upon z minus 2y. So here we get relation 6, relation 7 and relation 8. Any two relation we will solve. Then we find two solution u and v. Solving any two above relation, then we get two solutions. First solution is the function of second solution. Now solving equation 6. Taking first and second fraction from 5, then we get dx upon y square equal to dy upon minus xy. This is equation 6 or relation 1. Integrating on both sides to equation 6. So I am writing here integration dx upon, here is y square. Y square means y into y equal to dy upon minus xy. So 1y is cancelled here. Y is cancelled. We get here dx upon y equal to dy upon minus x. Now cross multiply. Here cross multiply. Cross multiply. So x multiply this by this. Minus x and y dy. So integration x dx. Integration is x square y. And integration y is y dy. This is y square y2. So here adding some constant c1 by 2. This is constant, arbitrary constant. Minus x square y2 equal to y square by 2. So c1 upon 2 equal to y square by 2 plus x square by 2. Now 2 is cancelled. Then x square plus y square equal to c1. This is equation 9. So we get u equal to c1. U equal to x square plus y square. X square plus y square equal to u equal to c1. This is first solution. Okay. And now finding second solution. So we will take any other fraction, any other two fraction from equation 6, 7 and 8. So we get this dy upon minus xy equal to dz upon z minus 2y. This is equation 7. Integrating equation 7 on both sides, then we get. So here is minus xy and here is x. So x cancel. So this implies that here dy upon minus y equal to dz upon z minus 2y. Now cross multiply this. So writing here z minus 2y into dy equal to minus y into dz. So here is z dy minus 2y dy plus y dz. This equal to 0. So here z dy plus y dz and minus 2y dy. This equal to 0. So this formula, this is formula. We can write d of zy and minus 2 this y dy. This equal to 0. Integrating on both sides. This is 2. Integrating both sides. So this d cancel to this. Here is zy and 2. Here integration y square by 2. Here writing c2. 2 is cancel. 2y minus 2y not. This is zy. Zy minus y square equal to c2. So this is solution. So here integrating z y dz z here 2y. So here 2y. So 2y y square y 2 is cancel. So we get this result. Zy minus y square equal to c2 and zy minus y square equal to b equal to c2. Where b is this? First form of complete solution of 1. Fu equal to 0. So Fu is x square plus y square and zy minus y square. This equal to 0. Or second form of complete solution of 1 is u is the function of b. U is x square plus y square equal to function of zy minus y square. Okay. This is second type of solution. This is first type of solution. We can write any type of solution. Both are correct. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.